This week we'll talk about binary search and meet in the middle. Binary search was covered earlier in week 3, but in a very simplified form. So here we'll look at a bit more complicated binary search. So the first problem we are going to discuss is the Leetcode problem: find the first and last position of element in a sorted array. So here's the problem description. So you are given an array of integers already sorted in ascending order, and the question asks us to find the starting and ending position of a given target value. And the requirement is that the complexity must be log n, so linear time is not allowed. And if the target value does not appear in the array at all, then return this -1, -1. So let's first look at the example. So given this target array 5, 7, 7, 8, 8, 10, if the target is 8, then the output should be 3, 4. So these are the beginning indices and the ending indexes of the segment that inside which all the elements are 8. So this is 0 indexed, so the 5 is the 0th element, 1, 2, 3. So the first index where 8 appear is 3, and the last index where 8 appear is 4. So we should return 3, 4. And if the target is 6, because 6 does not appear in here, so we should return -1, -1. So that's a problem, and you may want to pause the video to think a little bit about how you would solve the problem. Okay, so here's the code. We are essentially using binary search to find the first and last. We use binary search twice to find once to find the first element, the other to find the last, the first appearance of the target, and the second time to find the second or the last appearance of the target. So here the code is in C++ instead of the usually Java. So there is a reason for that, and I think most of the code are essentially the same. It's the same syntax. So we are given a vector of integer, so that's essentially an array list. You can think of it as an array list or just an array. So the value that we are going to return is going to be a size2 array. So I write the equivalent Java code in here. So essentially we initialize the answer to be -1, -1, so that in the case that the target does not appear, we can simply return this default answer. So in the binary search, we have a beginning index and an ending index. So here, beginning index set to be 0, ending index set to be the last one, so size -1. And very important, when you write binary search, there should always be an invariance. So when you are fluent in this, the invariance may be simply in your mind. But when you are just starting, you should write out the invariance in comment in your code. So here is the invariance that I'm going to use in this binary search. So I want to make sure that the beginning index, the first appearance of target, is between B and E inclusive. So the first possible appearance is B, and that means that the value before B, before the B's index, is less than target. So the nums B-1 has to be less than the target. So that's one part of the invariant. The other part is the nums E has to be greater than or equal to target. So we are trying to find the first appearance of target. So if these invariance holds, then the first appearance of target must be between B and E. And we are basically going to narrow this window. When B equals E, we have found it. So once we have this invariance, we have to make sure that invariance holds when we start the loop. So in order to do that, we actually have to first check for the boundary conditions. So the first boundary condition is when the array is empty. So if nums is empty, so then the size is 0, e will be -1. So in that case, then clearly the target cannot appear, so we will be returning -1, -1. The second case is because our invariance says num e has to be greater than or equal to target, so then we have to check whether num e is less than target. So if num e is already less than target, then the biggest number is less than target. So therefore, target does not appear. We can return -1, -1. So this red part is needed because it sort of ensure the invariance holds. This black part here actually is not totally necessary. So this is to check whether target is less than the smallest element. In that case, we should also return answer. But this is only a sort of a performance optimization. Even if we don't have this part, this will be caught later in the code. Basically, let's wait until this goes away. The last line in this code will find that situation and return -1, -1. So it's only a performance optimization. Okay. So now going back to this loop here of the binary search, so we'll be keep in here so long as b and e are not equal. So the ending condition is b equals e, and binary search we find the middle index, sort of the index between b and e. Essentially, it's b plus e over 2. So here I use this equivalent but slightly different logic. The main difference is that if b plus e is overflow integer, then the first logic is still correct, but this one is not. This is really very rarely this is necessary. So I think it's probably better I just use the b plus e over 2 here. But this is what I have, and it's equivalent. So then we will be comparing this middle element nums m with target. When we do the comparison, there are 3 cases. So if it's less than target, then that means the middle guy is already less than target, so we can move b forward. So based on our invariance, we want num b minus 1 to be less than target, so we should set b to be m plus 1. And the other case is if nums m is greater than target, then that means we should move the ending position earlier. So we set that to be m, because that will ensure the invariance, and setting this e to be m minus 1 will not ensure the invariance. So there's also the situation where nums m equals the target. So when we are doing binary search just to find the ending occurrence of a target, at this point we can already return, we can already be done. However, here in this problem, we are trying to find the first appearance of a target. So even though nums m equals target, we're not done yet. We only know the middle element is a target, but we don't know where is the first time the target appears. So because of that, we will be done only when m is already equal to the beginning. So then that means we have found the solution. So the first appearance of the element is m, which is also the same as b. So at that point we can break. So otherwise we will actually fall through the case of num m is greater than target. So we'll just move e earlier. So if the m's element equals target, then the first appearance must be less than or equal to that, must be between b and e. So we'll continue our binary search. So that's how this logic works. So yeah, the condition here is a little bit complicated because we want the first appearance. And when the loop we will exit the loop when under two circumstances. The first is B equals E. Then by the invariance, then if target appears, it has to be the first appearance has to be B. Of course, there's also the situation where the target does not appear. So in which case, we will still see B and E. We will still see B equals E and then exit the loop. But then the last line on this slide will check for that condition. So if nums B does not equal target, then we'll return -1. So note that this invariance covers that case. So it could be that when B equals E, what we have is B minus 1's the B minus 1's number less than target, and the B's element will be greater than the target. Then target does not appear. So the second case where this loop will finish is we find that M equals B, and the M's element is equals the target. So basically the condition here. So if we go past the last line on these slides, then that means nums B will equal to target. So we have find the first appearance of target. So let's look at the rest of the code. So at this point, we have already find the first the first appearance of target. So we assign that to answer 0, and now we're trying to find the last appearance of target. So we reset E to be num size -1, so the index of the last element, because the answer must be between B and E. So and we initialize the sort of default value to be just equals E, and we check that if E equals the target, then we'll simply, if the E's element equals the target, we'll simply return the value we constructed here. So the invariance for this part of finding the last occurrence is the solution will be between B and E minus 1. So so the invariance is the B's element equals a target, and the E's element is greater than target. So this holds because of the check here, and because of this, we will be, the loop will stop when B equals E minus 1, because that means B is the answer, because num B equal target and num so when B equals E minus 1, then E equals B plus 1. So num B equals target and num B plus 1 will be greater than target. So B is the last time that the target appears. So that's the invariance, and that's the loop condition. So they are sort of tightly related. You can do this using a slightly different invariance, and then your code will need to adjust accordingly. So again, here we find the middle element, and here we only care about whether the middle element is greater than target, because at this point we know it cannot be less than target. It will be either greater than target or less than or equal to target. So if it's greater than target, then we can move E earlier to the value of M. Otherwise it's equal, then we will set B equals M. So again, this will be the invariance will be maintained by this code because of the conditions here. So then when the loop ends, we will assign B to answer 1, and then we return. So my suggestion for writing code that does binary search is you have a clearly specified invariance, and in fact, I recommend you to write it down in the comment of your code and refer to it, look at it when you need to write other part of the code. And then you need to ensure that the invariance holds at the beginning of the loop, so before the loop starts. And then you also need to ensure that any update within the loop will maintain the invariance. And there's one other thing that I did not explicitly address. That is, you have to ensure that your loop will make progress. So depending on your loop update, it is possible to actually have an infinite loop. So let's go back, look at the code. So for example, here, if instead of doing b equals m plus 1, I just do b equals m, then I may have an infinite loop. Because suppose e equals b plus 1, so then this we will not exit the loop because b is still less than 1. So b equals e minus 1. Equivalently, e equals b plus 1. But then m will be equal to b. So when you do this, b plus e over 2, you will get the b because this is integer division. So then when you just assign m to b, you will be, and suppose that this condition holds, then b does not change. So in this whole loop, in this condition, b doesn't change, e doesn't change, so we're making no progress. So then we are essentially going to run into an infinite loop. And here, it cannot occur in here because I set the condition as b less than e minus 1. So at most, b will be e minus 2. So in that case, the value m cannot equal to b or m. So when b and e are at least 2 apart, then m will be the element in the middle. So it'll be somewhere in the middle. So m cannot equal to either b or e. So therefore, this assignment will guarantee to make progress. So with this assignment, then I cannot use b less than e as the condition. If I do, then I may run the code will run into infinite loop under some input test case. But if I change to b less than e, I need to change the code here. Then I need to change the invariant. So again, almost if there are 3 key parts: the invariance, the condition, and the update. So changing any single part is usually okay so long as the other 2 parts are consistent. But if they're not, then you have a bug in your code. Okay, so that's it.